Okay, for CRS, I'm going to start with Competency 2. So here's a question that refers to that. Given a matrix A, or a set of columns that can be put together to form a matrix A, use transpose and row reduction to find a set of linear independent vectors that span C of A. So that's the statement of the competency. Let me go ahead and do a couple of examples. So let me finish up with example 1. So in this case, just follow the instructions line by line. Here it says use transpose and row reduction to find a set of linearly independent vectors that span C of A. So I'm going to transpose this. So let me call this A. I'll call this B. So let me go ahead and transpose this. And by the way, you can go ahead and pause the video, try to do it yourself. So if I do transpose this, I'm going to get 4, 9, minus 2, 7. That's the first row here, and it becomes the first column here. And the second row here becomes the second column. 0, 2, 1, 4. All right. Now, if I row reduce this, all right, I can see that these first two rows are not multiples of each other, so they're linearly independent. That means the first two rows are going to row reduce to 1 and 0, and to the identity matrix, because they're linearly independent. The other way you can do is take the determinant, 4 times 2 minus 0 times 9, which is not 0. So this 2 by 2 matrix is non-singular. When it row reduces, it will go to the identity. Now if that's the identity, then that's going to take care of all the other rows. There's nothing else for the other rows to be but 0, 0, 0, 0. And you can verify that in fact this matrix does row reduce to this matrix here. So what does that tell you? This competency says that once you row reduce, the rows here turned into columns become a set of linearly independent vectors that span C of A. So this gives non-zero vectors, two non-zero vectors, 1, 0 and 0, 1. And if we turn them into columns, they become 1, 0, 0, 1. And these two vectors span the column space of A. Now that's really not a surprise, because the column space is the set of two-dimensional vectors, and these two vectors span all two-dimensional vectors. So let me just finish writing down the significance of this. Okay. I'll just say these two vectors span C of A. So I want you to note that these are not columns of A, but they span the column space. Previously we found columns of A that span the column space, but you don't necessarily have to take columns of A to be a linearly independent set that spans the column space. Okay. So these two vectors span, because, and you can say, even though they aren't columns. In fact, they're linear combinations of columns, so they themselves are in the column space, and they span the entire column space. Now, that's a pretty trivial example. Let's try the other one. The other example I have here is, all right, the first one is 1, 2, 3, 4, 8, 4, 5, 2. So let's write B down here. So B, 1, 2, 3, 4, 8, 4, 5, 2. I think that's right. Let me make sure. Yeah, we're good. Okay. All right, now we want to do the same procedure. We want to take the transpose, and that gives us, well, the first column becomes a row. We can think about it that way. 1, 2, 3, 4, and then 8, 4, 5, 2. So now if we're going to row reduce this, well, first thing you would take is R2 is minus 8R1 plus R2. That's going to give me 1, 2, 3, 4. And then this will give me 0, minus 16 plus 4, minus 12. Better be careful because I've been making a lot of mistakes. Minus 24 plus 5, minus 19. And minus 32 plus 2, minus 30. Okay, this one's kind of a nasty one, but that's okay. So I'm going to take R2 over minus 12. Serves me right. I just pulled it out of my head. So 1, 2, 3, 4. This becomes 0, 1, 19 twelfths, and 30 twelfths. Well, 30 twelfths is what? 15. How much does that go? 6 goes into both of them, right? So that's going to be 5 halves. All right. And then to finish this off, we would take minus 2 R2 plus R1 and get 1 minus 2 plus 2 is 0. Minus 2 times 19 twelfths is minus 19 sixths. Minus 19 sixths plus, how many? That's 18 sixths, minus 1 sixth. And then this is going to be minus 5 plus 4 is minus 1. And then here I have 0, 1, 19 twelfths, and 5 halves. Okay. So let's go ahead and take the transpose again. Transpose gives me first row becomes a column. 1, 0, minus 1 sixth, minus 1, 0, 1, 19 twelfths, and 5 halves. Okay. All right, so we have two vectors here, and according to the procedure, these two vectors specifically, I mean the two columns of this matrix, 1, 0, minus 1 sixth, and minus 1. Is that a minus 1? I guess so. And 0 and 0, 1, 0, 1, 19 twelfths, 5 halves. These two column spaces span the column space of A. Once again, they are not, that's column space of B, sorry, column space of B, because I started with B. Okay, span the column space of B. So I started with B, I took the transpose, did this row reduction, I got two vectors, and these two vectors span the column space of V. Now again, B, they are not columns of B themselves, but they do have a fairly nice form. They have this kind of row echelon form where some components are 1 and some components are 0. Of course, these are neither 1 nor 0, but they kind of correspond to free variables. But for this competency, just follow the procedure where you take a matrix, a transpose, row reduce, and transpose again, and the columns of the result is a set, and the non-zero columns of the result is a set of linearly independent vectors that span the column space of the original matrix. So there's some exercises you can practice on that.